Welcome to our lecture on exoplanets and the search for life beyond Earth, presented by Dr. Microlearning. In this talk, we'll explore how discoveries have accelerated, why certain targets matter, and the tools and strategies scientists use to sift promising worlds from noise, all with the goal of understanding where life might plausibly exist outside our solar system. Over the past decades, exoplanet counts have exploded, moving from a few tens to thousands, and now into the thousands plus, thanks to missions like Kepler and TESS and ground surveys. This slide shows that shift from early speculation to a data-driven research program, where large statistical samples let us plan targeted follow-up and prioritize the most promising worlds for characterization. The habitable zone is best thought of as an annulus around a star where liquid water can exist on a planet's surface, but its position depends strongly on the star's mass and brightness, and even shifts over billions of years. The diagram highlights how different star types change the zone's width, and how time variability can expand or shrink the regions suitable for life. Modern habitability moves beyond simple location and considers surface reflectivity, greenhouse effects, stellar activity, tidal locking, and atmospheric escape. These factors can shift the habitable zone inward or outward and dramatically change surface conditions. So assessing a planet's true habitability requires combining orbital position with atmosphere, climate, and stellar environment models rather than relying on distance alone. Transit surveys are powerful but biased. They preferentially detect large, close-in planets because those transit frequently and produce strong signals, which explains why short-period giants dominate confirmed samples. Earth-like orbits are harder to catch due to longer periods and geometric probability. So we must correct for this detection bias when estimating how common temperate, rocky planets really are. Radial velocity surveys add complementary detections but also favor massive, close-in planets by measuring stellar wobble, and when transit and RV samples are combined, hot Jupiters remain overrepresented. The takeaway is that statistical debiasing is essential. Only by accounting for these observational biases can we reliably estimate the true prevalence of habitable zone Earths in the galaxy. When choosing targets, G and K stars stand out because they offer stable luminosity and wide habitable zones that can persist for billions of years, providing favorable conditions for life to evolve. The slide shows survey alignment with these stars and notes that roughly 3/4 of habitable zone candidates orbit G or K hosts, making them priority targets for detailed study. M dwarfs present a mixed picture. They are abundant and long-lived, which makes them attractive targets. But their close-in habitable zones risk tidal locking, intense flaring, and atmospheric erosion. This slide frames that tension, emphasizing that abundance and longevity keep M stars high on the list, while highlighting the environmental challenges any life would need to overcome. Detecting atmospheric biosignatures requires next-generation telescopes with high-resolution imaging, broad spectral coverage, and enhanced sensitivity, paired with techniques like transmission, reflection, and thermal emission spectroscopy. The framework shown here stresses that simultaneous detection of multiple gases such as oxygen, ozone, methane, water, and carbon dioxide strengthens confidence by ruling out many non-biological explanations. Stellar activity can contaminate exoplanet spectra because star spots and plages mimic or mask atmospheric signals, so separating true planetary features from stellar noise is critical. The slide outlines decontamination strategies, multi-wavelength monitoring, polarimetry, and interferometry, which together enable reliable retrieval of weak biosignature lines and reduce false positives in atmospheric analysis. Current and future missions form a complementary pipeline. JWST delivers infrared transmission spectra now. ESA's Ariel will build a statistical census of exo-atmospheres. Proposed life interferometers aim for mid-infrared direct imaging of Earth-like planets, and a future habitable worlds observatory would target sun-like stars for true Earth analogues. Together, these missions move us from detection to detailed characterization. The roadmap ties technologies like coronagraphs for high-contrast imaging, ultra-stable spectroscopy, and advance data science into a 2-decade plan that aims to identify compelling biosignatures or, if none are found, refine our understanding of habitability limits. Successful coupling of hardware and analytics will either reveal candidates for life or set strong constraints that sharpen future search strategies.